Up audio, and I'm just displaying this thing here. So in the event that you miss a class, you should see something like this here. All right, so what I would like to start with is to show you guys go through a concept-based question with you. So on the bottom of this page here, bottom of the front, you see two people playing catch. And I often like to do demonstrations like this in class where I work with another person on this. Seppi, maybe I could work with you on this particular thing. Would you be okay? Yes. I'm going to play the role of Aristotle. So the guy on the left is not really Verlander. I replaced him with Aristotle. So I'm a Photoshop expert. You might not realize that that's actually not Aristotle. But that's Aristotle. You're playing the role of the catcher. Do you know who that would be? That's Newton. Thank you. So will you stand? I'm gonna throw this to you. Now, if I throw this to you, you catch it. Okay. Now, this is not your first day as a human, so you know that it takes force to throw a ball and it takes force to stop a ball, right? So I'm gonna throw this at you. You okay with that? Yes. Okay. So when I was in high school, I was able to do 3 sports, right? I was a 3-sport athlete, but that was when you could actually do those things where you could just play the sport during the season. I was a pitcher in the spring, so I can't throw it as hard as I normally would. But I'm going to exert force on this ball to throw it. It's okay, sorry. And it takes force for you to catch it. Now, if I use 25 pounds of force to throw this thing, so I'm going to use 25 pounds of force, about the weight of 3 gallons of milk. And then you stop that. The question is how much, if I use 25 pounds to throw it, how much force does it take for Newton, Seppi, to catch it? So you have 3 answers. 25 pounds for every action. There's an equal and opposite reaction. Definitely a lot more than 25 pounds, or somewhat less. A glove is used. We're going to ignore things like air drag. So if I can throw the ball at 70 miles per hour, ready? It hits your hand at 70 miles per hour. So we're going to ignore anything like air drag. You understand the idea? Would you take a moment and circle the answer you think is accurate? Which one best describes the amount of force it takes for Seppi or Newton to stop it? And then, if you would, just share with that person that you're sitting next to what your answer is. What do you think that is? So just take a moment to share that for yourself, and then share with that person. Yeah, that's where you need it. And then, if you would, try to return that at the end of the hour so they don't have a lot. Okay. I'm sorry. Oh, yeah. Are you? No, that's awesome.
So was my mom.
Is that right?
Yeah.
Pitching, I mean, a lot of things go through the picture. I was all arm. I never was taught how to use my entire body for that, right? Not for softball and stuff like that. There's much more of a wind-up portion there. Yeah. All right. Would you mind sharing? Anyone willing to share like what they chose and what might sort of explaining what they're thinking? You don't have to, but anyone willing to share? Okay. Let the record show no one raise your hand. How about this? Raise your hand if you chose letter A. Look around the room. You see almost everyone has their hand up. Okay, raise your hand if you chose letter B. You look around the room, no one has their hand up. Raise your hand if you think it's letter C. Okay, no one, you can't see this on video. No one raised their hand. Almost everyone thinks it's A. Okay, it's not it. Now, put an extra A. It's not it. But most people, and I want you to realize, most people think the same thing. And that's because we have heard some things in our lives that we believe to be true, and you may have even heard of that statement that for a reaction there's an equal and opposite reaction. It's called Newton's third law. Raise your hand if you've heard that before. Of course you had to if you're not a first human. But that's not the way forces work. But it's a misconception that when I throw the ball to Seppi, that I somehow give that ball force. And I'm giving it like 25 pounds, right? I'm giving it 25 pounds, and what I give it, you have to take away. That's not what happens. What I can do is I can give it speed. I can give it something called momentum. But I can't give it force, right? Force is something that I use to throw it. So the force I exert does not need to be the same as the force you exert. It's not A. Okay. So now that's not A. Which one is it? Is it B or C? Tell the person sitting next to you what you think it is now. It's not A. So which one is it? Okay. Now, since everyone thought it was A, you now have a different choice here. It's either B or C. Would you mind raising your hand? Now, you believe it might be B. B. Okay. Let the record show no one said it's B. Raise your hand. That means that it's C. Okay. Cross off C because it's not C. Okay. Now, but I want you. I use this as an introductory activity. A lot of us, you guys are all really smart people, and you try to figure out in your 16, 17, 18 years of life the way things work, and they're wrong. Oftentimes they're wrong. Okay, it's not A, it's not C. Which one is it? It's got to be B. Now, over the course of this unit, I'm going to try to show you why B is the correct answer. It's definitely a lot more than 25 pounds. As a matter of fact, if you want, I'm going to try to use your senses as a force indicator. So we're going to try this one more time. Okay. I want you to see if you can hear me throw the ball and see if you can hear Steffi catch the ball. Now, I don't want you to be distracted by the visual, so you have to close your eyes. Not you. You keep your eyes open because you're going to catch it. Close your eyes, see if you can hear me throw it. Close your eyes, see if you can hear Steffi catch it. Are you guys ready? Keep your eyes closed. Close them. Not you. You ready? Okay. You can open them. Could you hear me throw it? Could you hear Steffi catch it? The force of interaction is much bigger during the catch than during the throw. We'll talk about how that happens, but it is a common misconception. All right. So to help us sort of understand why it is, I'm going to ask you to do this for me. This is one of the things I like to do as well, is try to get input from students on some of your background, some of your histories. Down the very bottom of this page, you see the bottom thing here, it says on soccer day. I want you to think of the largest force you've experienced maybe in your life, a scenario in which you felt a large force. I would ask you to briefly describe it. Now, the description's very brief. I use it on SoccerDiv. So my SoccerDiv account is over here, FESOQZUZT. I would ask that you think of a situation in which you felt a large force, and then briefly describe it, a sentence or two. And then what I'm going to ask you to do is you're going to have access to 26 or so different large force scenarios. I'd just like you to look through there, see if you can identify a pattern. What is it that's true about large forces and what happens during those large forces, okay? Can I share mine with you really quick? 2 days ago, I fell on that step. That really gave me a really large force in my rib cage. That was the situation where I started slipping on the ice. Prior to that, it was in high school. I was a football player. I was during a kickoff. I was running full tilt down the sideline, and I collided with another person. I won't actually collide with you here. I think I would lose that battle. But over here for a second. I was as my height, but I was about 50 pounds lighter than I am now. So it happens with age. But I could run fast, right? The guy I collided with was about your size, pretty fast. He had probably about 50, 60 pounds on me at the time. We were running full tilt, lots of speed coming in, boom, hit. I saw stars for the first time. I mean, I really saw stars. I'm sure I was concussed from that. We didn't know about concussions at the time and stuff like that. So, we didn't know. My coach said, just we'll run some dirt on it and get back in. So I'm sure I was concussed. That would have been my situation if it wasn't for 2 days ago when I fell and landed on the steps. Do you have a situation in which you felt a large force? Would you take a moment, go to SoccerDiv and just type in a sentence or two describing that situation? Okay? We're going to look for patterns to see if we can find them. FESOQZUZT. Okay, so I'm going to hide the names. I don't know why I said hide names instead of showing the names. Huh. Okay. That's it. So as you guys do this, the things are going to be shown up here. I'm going to start a vote after we get most of these things put in there. I'll have you vote for, and just sort of, you would vote then for the one that you think is most, most interesting, if you will, of a large force. Okay, so again, just take a moment. Oh, guys, that's something I need to emphasize. Anytime I'm putting something up here where everyone's gonna see it, make sure it's school appropriate. Please don't put anything up there that would be like, just wrong for a school environment. So just make sure it's school appropriate. Okay. All right. Keep going. You can't see these right now because it's too small, but I'm going to put it out there for a vote so you can see them. I love the cow one. Okay. I'm sure there's some interesting backstories to some of these things. Okay. Anyone still typing? Still typing? Okay, I'm gonna stop. I'm gonna ask you to do a vote. This way you can actually see these things. So I have one of those really nice pencils for the winner of this, right? So vote for the one. I'm gonna start the vote. Vote for the one that you thought was that you think is most interesting kind of scenario. Can you guys see it now? Can you get? It doesn't show the names, does it? Okay, just read through those. If you find one that you think is interesting, vote for it, and then I will give the winner of that one of these really nice fancy Ticonderoga pencils. They're pretty nice, right? So I bought these things just sort of as a little reward for you. So if you win it, that's yours. Yeah. Some of these are quite. All right, anyone still voting? Still voting? All right, looks like we have a winner. And that winner is at 27% up there. That's pretty funny. Pretty good. 27%. It looks like that's 26% now. I got in between a cow and a gate and was stuck. It's pretty fun. Unfortunately, we're going to know who you are because if you want to collect your pencil. That was you. All right, so thank you. What's your name again?
Kayla.
Kayla. So Kayla, you got stuck between a cow and a gate. Can you describe a little bit more? Thank you for sharing something so fun.
Well, I work on a dairy farm, obviously, and we were hauling cattle, and we were all, in a big group, and I got stuck in between one because it seemed like she didn't make it at all. So.
Yeah. Okay. Pretty. Could you estimate how many pounds of horse you might have?
Probably 1,000, 1,500.
Okay. Yeah. All right. Good. All right. So thank you. You won that one. It wasn't exactly the kind of scenario I was looking for. I was looking for more of one of these things, but that's okay. You won the prize. I like to do that. When you take a look at those 20-ish or so things, do you see a common like underlying principle here? That it is the suddenness of change. Now, not for you. Suddenness of change in motion. Can you guys see that? And most of these things here, there's a very sudden change in the motion of an object. That forces often are large when the motion changes occur very suddenly. I want you to consider that this is a very underlying, very common idea about physics, is that when I use force to throw this ball, look at how quickly I change the motion of this ball. It goes from 0 to 70 over an eternity of time. So look at, there's a time element here. 0 to 70, and it takes me about 0.3 seconds to do it. When Seppi catches it, it goes from 70 to 0. Are you ready? It goes from 70 to 0 nearly instantly. And it's the rapidness of that change in motion. It's the rapidness that's tied to the large force. So I'm giving it some force, I'm using some force to throw it, but that force occurs very slowly over a long period of time. The force you exert occurs very quickly, right? Very quickly, and it happens very suddenly. A large force. When I fell on that step, my body came to a very sudden stop. When I ran into that person on the goal line, or on the sideline, I came to a very sudden stop. And it's that sudden change that's tied to the large forces. So when I consider those kinds of questions about what force, who exerts the larger force, that underlying principle about suddenness of change is a key part of a large force. And hopefully you guys saw that with those 20 some odd. Not yours. Yours was more of a pressure idea, right? And pressure is related to forces. But, and you probably felt a lot of the weight of the cowl. But that's not the collision force. But that's okay. There's other things behind besides that. All right, so thank you for that. All right, so there we go. Now, I want to go back to this here, and again, folks, a lot of this stuff in the beginning is just to sort of introduce the concepts here. Here's the project. So inside the cover, egg drop. We're going to begin with the end in mind. You're going to build and evaluate or analyze. You're going to build and analyze the performance of a device designed to minimize the force of collision. You're going to try to make the force be as small as possible. You're going to try to protect the egg. The goals. I want you to rely on the laws that we developed through the unit. So oftentimes people are like, well, when am I ever going to use this? Well, the nice thing about the projects is that it gives you immediate use of the laws that we're studying. So instead of me giving you a pencil and paper test and you choose C for the correct answer, you're going to show me that you understand this by designing an egg drop device that is there to try to minimize forces of collision. I have one here from kids from previous years, and so this one was from Caitlin and Gabby. So Reliant Laws developed during the unit. I'm going to have you try to optimize through something called engineering. Now, a true engineering kind of preparation would involve all of those equations. We don't really have that, but I can still show you the process by which engineers would go through and try to optimize, try to make things better. And then finally, we're going to apply something called test to failure techniques. So test to failure is very common in industry to say, well, let's build this thing and then test it to see at the point it fails. For the bridge thing that I had up yesterday, they might build a bridge and then continue to add more and more weight to it until they determine the point at which it fails. They wouldn't do that for a real life setting. They'd do that as a simulation because it would be far too expensive to build a bridge and then have it fail. But when you see a failure mode, it's called failure mode analysis. When you see a failure mode, you can then look at that and say, we're going to try to protect against that failure mode, and then try to improve it. And this is how we sort of get better and better products over time. Right? So test failure. What would that look like for you guys? You're going to build your device. You usually do this as a group, right? So you choose a partner that you want to work with on it. You build it, and then we drop it from 1 meter. So there's an egg in here, imagine. There's a tough project to do this year because the price of eggs right now is just through the roof. But we'll supply you the egg. You drop it from 1 meter. It comes to a sudden stop. You're trying to minimize the force of collision. You guys see how these rubber bands in there are time extending devices? Those rubber bands might be used to try to extend the amount of time it takes to stop that egg. And so that makes that force smaller. Okay. You're going to try to build. If it survives the 1 meter, then we go to the 2 to 3 meter drop. So we're going to, you guys agree that it's going to be traveling faster if I drop it from a higher height? So we're going to test it under a higher condition. So often we'll have people stand on the table, do this, we drop it from a certain height. If it survives that, the ultimate test that we can do here is to simulate sort of like a 20-mile-per-hour collision, and that would be off the balcony out there. And so you probably have seen classes out in the balcony dropping these things. The goal is not just to build it, but to analyze how it behaves. I'll have a high-speed camera on it. We're going to look at how that egg sort of moves throughout its motion. And then from that video, you're going to try to, I'm going to show you the laws that underlie this. I'm going to show you how to calculate forces. And so that would be a part of your analysis. Okay? That's the way that this project works. sort of a fun project. Kids, I ask kids all the time at the end of the season or end of the course, what's your favorite project? A lot of them will say the egg drop was one of their favorites. Others like the speaker that we built and stuff like that. But anyway, you'll probably find something that you like. Okay, our last thing that I want to go through with you, this is it. And then once I'm done with this, I'm going to play some music and have you guys finish up your vanity plate and whatnot. If you didn't get the intra-survey stuff done, this is the last thing. Okay. So which of the following, raise your hand please, you've been in a car crash? About half of the class has been in a car crash. Raise your hand if you haven't been in a car crash. Raise your hand if you think it's likely at some point in your life you'll be in a car crash. Yeah, it's very likely. Right, the odds are that you're going to be in a car crash at some point. I've never been in any serious ones. I've been rear-ended and stuff like that, but there was nothing too serious. Which of these things, I have what, 7 of these things up here. Which of these 7 factors do you think could impact the amount of force you would feel, not your car, but the amount of force you would feel during a car crash? So I have 7 things up there. What I'd ask you to do is just read through those 7. I'd like you to do this individually first, and then I just have you share with people at your table. Which do you think could impact the amount of force you feel? Okay. Take a minute or so, read through those, circle the ones that you think could impact it, and then I'll have you share after that. So just take a moment. I'm going to walk around just sort of see where you are with this stuff. So please circle the ones that you think would be there. Once you're done circling, maybe talk with that person that you're sitting next to. See if you are in agreement with what they have. You don't have to be. You don't have to even explain your positions at this point. Just see if you are in agreement.
I just said, what you know how fast we're traveling?
Yeah. Yeah.
Yeah.
Okay. Hopefully you've had a chance to be able to do that and walk around and saw a couple of them. Raise your hand if you and your elbow partner had the exact same ones prior to you sharing. Just a few. That shows us that there is a wide range of ideas here. And most of us, in some cases, we just have to guess. I want to go through these 7, and I'm going to tell you which ones really would impact it. Over the course of this unit, I'm going to try to show you the underlying physics behind those. Right now, you just want to know which ones, but I'll show you the physics behind it. Okay, that's one of my goals here is to show you how that works. All right, so would you mind raise your hand, please, if you did identify that one, how fast you're traveling? Absolutely, that's going to impact the amount of force that you feel during a collision. If you're in a 60-mile-per-hour collision, that's different than if you're in a 10-mile-per-hour collision. Okay, so speed definitely impacts that. Raise your hand if you have the 2. No, don't raise your hand if you have the 2, but this will not impact it. Now, it might determine whether or not you are in a crash. Which one do you think you're more likely to be in a crash in? If you drive a 2-wheel or a 4-wheel? What's the obvious one? What's the obvious answer? You're going to be more likely to be in a crash in a 2-wheel drive. Is that true? If you look at the studies, there are more collisions with 4-wheel drive vehicles than 2-wheel drive vehicles. And the reason for that is that the 4-wheel drive vehicles drive way too fast for the conditions because they think that because they have 4 wheels moving them forward that they're going to somehow be impervious to the effects of friction. And they drive too fast for the conditions and they end up usually sliding off the road, especially with slippery roads like this and hitting a tree or ditch or something like that. They get into car crashes a lot. 4-wheel drive vehicles are really good at getting you unstuck. But they're not any better keeping you on the road than a 2-wheel drive vehicle. So people just drive too fast. Right? So if you're in a 4-wheel drive vehicle, slippery road conditions, you have to slow down. They will get you unstuck, but they won't keep you on the road. You got to be careful of that. Right. What you yourself hits, raise your hand if you had that one. Whether or not you hit the steering wheel, the dashboard, or the airbag, that's definitely going to impact it. So if you got that one, that's correct. That airbag is designed to help lessen the amount of force you experience That's similar to me using a long time to throw the ball versus if you hit the steering column, it's a very sudden stop and you throw a much larger force. So yeah, that will impact it. Full moon versus new moon? No. However, there's been studies that show people are more reckless during full moons. They drive with, I don't quite know why, but there are studies that show that during a full moon, people are a little bit more reckless, so it might improve the probability that you're in a crash, but it won't affect the amount of force that you feel. How about the mass or weight of your car? Raise your hand, you did that one. Yeah, it's going to impact it. How much stuff you're bringing with you in that car. If it's a really big SUV versus a small, Honda Civic or something like that, that's likely going to impact the amount of force you feel during a car crash. That will play a role. Manual versus automatic transmission? No, it's not going to affect the amount of force you feel. However, what's the problem with someone that said once to me when I talked about this one, they're like, well, I don't know how to drive a manual. Raise your hand if you can drive a manual transmission. Stick shift. Just a few, right? Yeah. A lot of people have a hard time driving stick shifts, but they're fun vehicles to drive, but you have to pay attention. You have to do a lot more. You got 2 feet going on. So you might not even get into a car crash if you have a manual transmission because you can't get out of the driveway. All right, and then what your car hits. Yeah, definitely. If you hit a trash can, you hit a bug, it's going to be different than if you hit a car. I'm going to show you the underlying physics behind those things. How many people had all 4 of those? Just those 4. Just those 4. Okay. That right there is your gut reaction saying these things will help you, these things will affect the amount of force. I'm going to show you the underlying physics so that your gut is right in these cases. Many times it's not. But if you got those right, your gut's right. Okay? I'll show you the underlying physics. All right, that's where I'm going to stop. Folks, we have, 9:17? We go till 9:29. You have 12 minutes. If you didn't finish the vanity plate, I would ask that you work on that next. If you didn't get the interest survey done, that's what I'd ask that you work on. If you're done with all of those things, you can chill, you can, whatever it is, that's fine, but please get those things done first, okay? Yes, I'll get you more. Okay, very good.